Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at Chapter 3, which is volumetric properties of pure fluids, and in particular, we're looking at generalized correlations for liquids. So as we discussed in class, for saturated liquids, we can use the Racket equation, which is based on VC, ZC, and TR, which remember TR is T over T sub C. And this is going to allow us to calculate the saturation specific volume for a liquid. It's a rough estimate. It's not very good, but if you're desperate, you're desperate. The values for ZC, TC, and ZC are all available in Appendix B from our textbook. And this is a way of getting one data point. If the temperature or pressure are different than that saturated liquid value, then we can make corrections using the Lydersen chart. And you can do this either from a fixed point from the Racket equation or a fixed point from data. Doesn't matter. But this Lydersen chart is in terms of the reduced density, which is density over the critical density, or in our book we have critical volume, so critical volume over volume would be the equivalent. And then we use the chart, we'll find our value for PR, we'll find a TR to choose one of these curves. If we read straight up from a fixed pressure until we find the correct curve for our temperature, where those intersect, I read straight across, and that gives me my value of the reduced density. I can then use two values of reduced density with this expression to come up with my specific volume at a temperature and pressure different than my known value. So let's look at an example. We're going to look at acetone. And when I looked up in our mass and energy balance book, at 20 degrees C in 1 atmosphere, the specific gravity is 0.791, and we have the critical temperature and pressure given, and we want to know the specific volume. So I need to get density, and remember that density is specific gravity times the reference density, which is just for water. So 0.791 is my specific gravity, and for water at 4 degrees C, we have 1,000 kilograms per cubic meter, or 791 kilograms per cubic meter is the density. And so the volume is 1 over this. So the reciprocal gives me 0.001264 meters cubed per kilogram. Now let's compare that to what we would get using the Racket equation for saturated liquid at 20 degrees C. In this case, I'm going to need additional data. So from the appendix of our book, Appendix B, VC is 209 cubic centimeters per mole, ZC is 0.233, and the molecular weight, I'll need that to go from moles to mass, is 58.08. The formula requires T sub R. T sub R is the temperature, so 20 degrees C, but remember I have to work in absolute temperature, so I'm going to add to this 273.15. So now these units are Kelvin divided by 508 Kelvin. So my units top to bottom now cancel, and the reduced temperature is 0.57677. Vsat is that formula, the Racket formula, so 209 cubic centimeters per mole. I don't want moles, so 1 mole is 58.08 grams. 0.233 is Z sub C. I'm going to raise that to the power 1 minus 0.57677, my TR. That is going to be raised to the 2/7 power. And VSAT, therefore, is 1.15 cubic centimeters per gram, or 0.00115 meters cubed per kilogram. And that's about a 9% difference from the data at 20 degrees C, 1 atmosphere. Now, granted, that's not saturated at 20 degrees C and 1 atmosphere, but usually volume is going to be a strong function of temperature and a weak function of pressure. So I would expect these to be closer than plus or minus 9%. But now, what we really want to know is what's the specific volume, and I don't want saturated liquid. What's the liquid specific volume at 100 degrees C and 50 atmosphere? So our fixed point that we have, let's use the one from the data book. And so we had that V was equal to 0.001264 cubic meters per kilogram. And V sub C, well, okay, now remember they gave us 209 cubic centimeters per mole. So 209, and then I'm going to divide by the molecular weight. And then I want to divide that answer by 1,000 to get 0.003598 meters cubed per kilogram. And so therefore, rho reduced is VC over V, so 2.85 is rho sub R. But I also need to know what it is at this condition. So I'm going to use the chart to get my second value. So for this one, T sub R is 100 degrees C. Remember, it has to be in Kelvin, divided by T sub C. And in that case, it's 0.734. And P sub R is 50 atmospheres over 47. Okay, both of those are atmospheres, so the units cancel. 1.06. So if we come over here to our graph at 1.06, so I'm, somewhere in here. And let's see, TR is 0.73, so I'm somewhere in here. And maybe 2 point, wow, okay, I did a poor job of estimating there. I'd say about 2.45. Now your estimate may be a little different from mine. So we're going to use that to estimate V as the V that I know, 0.001264, times rho sub R for my new state divided by at my original state, 0.00147 cubic meter per kilogram. So that gives us a way of estimating the specific volume at new temperatures and pressures. You're only going to be doing this if you have a fairly large change in temperature or change in pressure. In this case, I had a significant change in pressure and a modest change in temperature. And so in that case, it's worth this, but realize that the quality of what you're reading on the graph is going to be pretty poor. And so therefore, we'll just use the known data if I have small changes in temperature and pressure. So this concludes our lesson on liquids. Thank you very much for your time.